Okay, all set. You're ready.
Okay. So I'm going to talk a bit more about CROCO now, well, because it's a CROCO classes. So I'm going to talk a little about the way it is implemented, the way it can be used within CROCO. And it's, well, basically I'm talking about the same thing that I presented before, just it's more on the code side. So I have some reminders about waves and about bottom boundary layer, exactly like before. And then I talk about what is the capabilities in the model, the different model of sediment we have, and then about the implementation of CROCO, the equation, the cost structure, the different options. So actually those are the same on a different angle. I mean, it's more and more practical. So I describe the equation for those interesting, then where it is implemented in CROCO, and then how you can use this. Then a bit more detail about the use of it, but it will be mainly on Guillaume's side, which will go through the different test cases to explain a bit what it is, and I have a few examples. So about ocean and sediments, so the way they interact. So here we are here with the CROCO, well, the CROCO you know, basically the one which can be to do open ocean modeling. And what we need to do sediment, we need some wave data, because we are mostly, well, because wave play a key role in sediment modeling. So we need to be either coupled to a wave model or to have offline wave data. And we need a description also of the bottom boundary layer, which is not what you are doing when you are using ocean for open ocean. You are using some kind of a standard bottom friction. So this model of bottom layer is included inside CROCO and sediment model also. So I think I won't go into a test. I think you saw this with Swen. So in the presence of wave, the set of primitive equation takes a different form with additional terms which are there on the right. So what matters here is the tracer equation there. So the sediment will be transported as salt, as temperature. So with the standard equation and some additional terms, which are due to waves, some are due to waves, some are specific to a sediment. And actually, we will be interested in the waves equation, in what is happening there. So the bottom boundary layer and the variation of orbital velocities. Yeah. So the bottom boundary layer, so here bottom stress matters because there is will play a role in erosion and suspension of the sediment, the water column, play a role in bed load transport also, what we saw before. And the sediment will play a role on the roughness of the bed. So it will change also the bottom friction. So for so we have, you know, those classical formulation for the bottom stress. So here, for instance, it's a quadratic stress, where stress depends of coefficient and of the norm of the velocity. We got also eventually some logarithmic stress, so with this kind of shape, whereas Z0 is an arbitrary constant, which is a description of which is constant and the description of the roughness of the bed. But you can see here that we have nothing related to the bed and nothing related to sediment either. So that it's not enough to be able to describe, to deal with sediments. So we have to take into account the stress, the current stress, the mean flow stress at the bottom, but also the wave shear stress, and we need also to have a sediment dependent rugosity. So what is done in BBL is to take wave currents, to compute wave current stress, which is a mixture between the pure current stress and the wave stress. So the pure current stress is the same, is this one, the one you would have without wave, and the one which is due to wave friction is here. So at the end, this term is designed to give a strong weight to wave friction when a wave fills the bottom, and stronger weight to the current offshore. And this will allow us to deal with wave friction and wave-induced motion of the sediment. So the different model we have. So we have two models available within CROCO. We have one model which is there since a long time, which is a model originally developed at USGS in the US. It's a kind of legacy model in terms of historic. It was already before CROCO, it was Ramsavif, it was there. It is also available in Rams-Rutgers in a cost version from John Warner. And it's very close to the one which is implemented in COST. And this one can be activated with PPK sediment. And what we got since 1 year, we also include a model developed at IFREMER, so it's a French institute, and this model is called Mustang. So it was originally included in Mars 3D, which is a French model. It is just released, but my talk and Guillaume's talk and the tutorial are mostly about the USGS model. So I would say that both models focus on non-cohesive sediments. Maybe Mustang is most used to do also cohesive sediment. They are both describing the same processes, at least at the first order, with some difference in sometimes processes or numerics. And in USGS, we have developments underway for cohesive processes. But anyway, if you're interested in Mustang is documented in the CROCO documentation. And the test cases are designed to work with USGS and Mustang. So you can activate one of the other, even if I think Guillaume will present only USGS. So the main process described in CROCO, those are the process we saw before. So those are the transport in the water column, erosion of the sediment, deposition of the sediment, transport through bed load, and then the bed itself evolution. So the composition of the bed between the different sediment, and then also eventually the morphological evolution of the bed, so a change of the bathymetry in time. So about the implementation, so for each class of sediment in the water column, you have this equation. So this is the evolution of the sediment, this is advection, this is mixing. So it's the same as any other tracer, temperature, salinity, biogeochemical tracer. But we have additional term corresponding here to the settling of the sediment and here to the erosion of sediment. So this is a sink term, this is a source term of sediment. And just to say that the velocity considered here is a Lagrangian velocity. So it's we are in the wave average context as we saw, so the velocity, the mean current velocity plus the Stokes velocity. So there is nothing to do especially for to take into account Stokes velocity because it's already included there. So, and each sediment is a tracer, which is described by the grain, by some parameters, the grain size, the density, a settling velocity, an erosion rate, a porosity, and a critical stress for erosion. And maybe what can be specific is you may want to use a positive advection scheme or a monotonic advection scheme to avoid creating overshoot and negative concentration of sediment. So there are some available within CROCO. And the boundary condition at the bottom and And at the surface are zero flux condition. I mean, the flux at the boundary is in this term, at the bottom is in this term, and you have standard lateral boundary conditions. So you can, in your boundary files, your input boundary files, add a concentration of sediment from the simulation and so on. So for this term, the term of settling, so this is a sync term, and which and this velocity depends of the class and basically on the size of the sediment, and it's an input parameter, as we saw, for the model. So at each sediment, there is associated a settling velocity. And actually, so this is so for the sediment, we got the classical vertical advection, and in addition, we got a second advection, which is due to the gravity, the weight of the sediment, and those both are treated separately. Then about erosion, so in non-cohesive case, we got this erosion rate, which is a source term, so sediment which will be eroded at the bottom will go in the water column. And this erosion rate is an empirical function that can be described by this kind of formula, for instance. So here it's a constant here. P is the porosity of the sediment, so it's a fraction of sediment, it's a fraction of water content inside the sediment. Tau here is the shear stress, so it's the stress which is calculated by BBL. So this is a stress due to current, a stress due to wave, and there is a critical stress above which sediment will be eroded. So this is the case for non-cohesive case. This is the case for non-cohesive sediment. So it means that non-cohesive, it means that sediment in the bed, they won't aggregate together, and they will stay in the bed as something like individual particles. But we also have something which is new enough inside the CROCO, the case of mixed or cohesive bed. And here it means that in the bed, you can have a sediment with cohesive property. So it means that the erosion capacity of this sediment will be a property of the sediment layer, because the sediment will get more compact, there will be a consolidation, and the sediment will become more difficult to erode. And basically, what happens if we see there on the right, there is an ideal profile for erosion. There is a standard profile for erosion and deposition, and there is dumping of this term of erosion and deposition toward toward an empirical equilibrium profile. And for instance, also what is described here. So if we take the cohesive behavior of sediment between 0 to 1, and we take one layer of non-cohesive, one mixed of the two, and one cohesive, will be here a stress which will be constant, which will be constant, then variable, the mixed zone, and then constant. And so in the mixed case, so we have a stress which is a mixture between the cohesive stress and non-cohesive stress. So for the bed load implementation, so the bed load, so this is the phenomena where the sediment is moving, but not in the water column, still in the sediment column, just by rolling or by a small salt like this. So this phenomenon is not resolved explicitly because of scales. It's a bidimensional phenomenon which are with X and Y components. And this is something which is not very well understood, which is with only parameterization And there is no real consensus about this. So for this, we will define a bedload flux, which depends also on the density of the sediment, of the size of the sediment, and with an empirical function there, an empirical transport rate, actually, with different options. And there is also a slope effect, so which take into account what could be seen as avalanching. So when the slope of the bed becomes too steep, you will have some sliding of the sediment, and this term depends on the slope with some arbitrary constant. So for bedload, we got several parameterization. I think I have two here. There is one very old formulation, which is from the, I think, 30s, something like this. There is a formulation which is actually advised in case of rivers or on the shelf. And actually, this is often for linear waves, because this formulation doesn't take into account the non-linearity of the wave, and it was actually developed by analogy to the transport of gravel into rivers. So we got, for this one formulation, so we compute this transport rate, where 2s is the shield parameter, so the capability, the instability of the sediment, and there is also a critical shear there. And what we use to compute this shield is the shear stress of the fluid. And we got another implementation, which was developed more recently by van der Haar, and it is advanced in terms of non-linear waves, because it takes into account the wave effect, the asymmetry of the wave, and the shield parameters induced by wave. So I won't enter into the details there, but let's say that this is the one which is advised in the nearshore zone, for instance, all the examples I showed in the previous presentation. And in terms of morphodynamics, so as we saw with sediment, we got erosion and deposition of sediment. So the bed is moving, so the bathymetry can move. So I'm saying can move because it's not mandatory to have the bathymetry moving. If we consider, for instance, that the water column is high enough compared to variation of the seabed, you may do the approximation that the bed is not that the bathymetry is not changing, and you just you make a small mistake, but you revisit. But if you want to compute the morphological evolution, so as we saw, the morphological evolution is the divergence of the transport. So you got here the transport in the water column at the last level. So here it's erosion and deposition, so it's a variation of the bottom. And so it's just for the record, this implies that we have a vertical velocity at the bottom, but it's transparent for users. And we've got these factors which can be used to speed up the morphological evolution. For instance, imagine you want to simulate an evolution at for 100 years for a beach, for instance. You can increase this factor, and the seabed will change faster. So we get a result. You get your result faster, but you won't change the amount of sediment in the water column. It's a kind of trick, but it's working actually pretty well. So this is, for instance, working to there. So this is a validation with a flume experiment in Grenoble. So this is the initial model. So in blue, blue, there are the observation. In a dash, there are the observation. In blue after 12 hours. In pink after 1 day. And you can see that it's worked pretty well. It's something we spent a lot of time to avoid instabilities and so on. And then, so we make the bed evolve. So the bed is defined when we are using sediment. So we got our 3D array corresponding to the ocean, but we also got 3D arrays under the ocean corresponding to the different sediment layer. And this is, we have a fixed number of layers in a CROCO for, while the user can change the number of layers, but the number of layers won't change during the simulation. So here, for instance, we got seven layers of sediment. So when there is erosion of sediment, so this layer will disappear, so the above layer, and this one will be split in two to keep the same number of layers. And you will see here that the bed change actually, that it is deeper. And when there is deposition, it's the same. If there is enough deposition, we create a new layer, and we merge the layer at the bottom to keep a constant number of layers. So in terms of implementation, so I will talk here about the cost structure, but I will talk about the exact same thing than before, just explain why it is in the model if you want to go into it. So if we take the time stepping of CROCO, you have the standard time stepping. So you begin by read your data and so on. You compute the barotropic mode, then baroclinic mode, and then the tracer part, temperature, salinity. And with sediment, you just call sediment at the end. So in this part, you have transport the water column by sediment, and in this part, you have all additional phenomena. So evolution of the bed, settling, erosion, and bed load. And then at the beginning of the time step, you got the shear stress, which is updated from the roughness of the sediment. So in sediment, things are done in this order. So this is only one big file actually, with different routine inside. So we begin to compute the bed load, then settling of the sediment. So we accumulate sediment at the bottom. Then the erosion of the sediment and the budget between erosion and settling. And then we make the update of the sediment layer, what I showed just before. And then just before the end, we change the rugosity of the bottom to be able to compute again the shear stress. So but just I will go quick on this. But so this is deposition. This is a deposition erosion routine. So there are exchange between water column and seabed. So we have the bed stresses, the shear stress, and we'll compute some erosion based on this shear stress. When this stress is above the characteristic sediment, the critical stress for the sediment, and we'll inject sediment in the water column at the last level of the model. And then in a set bed, we'll update the different sediment layers. So I won't go into the detail for this one. And in terms of model options, so you have option for BBL. So you need, it is feasible. In terms of computing, the model will run with sediment if you don't activate BBL, but I don't think it makes a lot of sense because you don't have any effect of wave. So with BBL, the SPP keys, just call BBL. So if you don't have wave input data, if BBL is activated, you will have a constant wave put by the model. something like a wave characteristic, like 1 meter waves with a 10-second period, something like this. And those waves will be used all along simulation. If you have wave forcing, or if you're running a coupled model with waves, you will use the wave data from the other model. And then it's what you can see here. If you are coupled, or if you have forcing, or if you have the built-in wave model inside the CROCO, you don't define any wave. And then the other option, you don't have to change it. For the sediment parameters, so if you want to use sediment, you have to play with several places of the code. So the number of sediment and the number of layers are hard-coded in param.h. What you can see there. So here it's hard-coded for some of the test cases. So you've got the number of layers of sediment. So it's those are layers which are under the seabed. So here 11 sediment layers. And you got only one kind of sediment, which is only sand. So, and here for this one, you have 2 and 10 layers. For this one, you got a lot of layers. You got sand, but you got also those sediment, which are some kind of what we call mud, is a sediment with a cohesive property in the bed. So you have those parameters, so and sand, and mud and grav and lay to change. And number of sediment is the sum of those three. And in terms of CPP keys in CPP dev.h, you don't have a lot of keys for, I would say, standard users. You have to choose between USGS model activated with sediment or Mustang model activated with key Mustang. And then for sediment, USGS model, you can specify if you want to do suspended load, so transport of sediment in the water column, or and bed load, so transport due to grain interaction. And so you can see that you got pre-selected options, which are the different bed load functions, for instance, and I would recommend to stick with the default choice, just to change between those two. Usually people, they do anyway suspended load and check if you want to do a bed load too. And with sediment, you got also an additional text file to describe the properties of sediment. And it has to be consistent with what was defined in param.h file in terms of number of layers and number of sediment classes. So I think Guillaume will detail this file for each test cases. So I put just some lines. So here it's a case with two, I think it's 2 kinds of sediments and 2 layers. So for each sediment, you specify the initial concentration in the water column, the density, the settling velocity. So here it's a coarse sediment. So it has it's heavy, it has a higher settling velocity. We specify the erosion rate and the initial bed fraction in each layer. And then some other things you may not want to touch. And then just a few examples. So here it's a study which was done in Vietnam. So this is Vietnam, this is the South Peninsula, this is the Mekong Delta, and we use the sediment model to study erosion deposition all along the delta. Here we have the Mekong, so we got a source of sediment there, and there is some erosion here, and sediment are deposited here in this area. Those are satellite observation, and you can see well at first order it's matched pretty well. And the example is still in Vietnam. So this is more when we're going near shore. So here again, this is near Natrongaraya. There is a river mouth here at this place. So here at the observation is the coastline. So in blue, it's in 7 in 75. In red, it's more recent in 91. And what we see, the creation of the sandbank here due to sediment coming from the river. And we can see that the model succeed to create also a sandbank here. And another study was done also in Senegal. So this is Dakar. This is a so-called Langue of Barbarie. So this is a narrow sand location, which is eroded by the wave coming here from offshore. And President Macron went there and promised to save this place. So we had some funding for this, and we studied the effect of putting some construction somewhere, if it was efficient to stop erosion and so on. And the third example, it's one which is very specific because it does not take place in the context of wave average model. It's a configuration where we actually resolve the phase of the wave. So it's a very, very fine resolution, centimetric resolution, and a very, very small time step. And there was some experiment in Delft in Netherlands in a real size flume, where you simulate with bathymetry, you simulate different wave scenario of wave condition. So energetic waves and low energy wave. And we had a look on the evolution of the seabed. What you can see there, for example, for the high energy wave, you got some erosion. You got some erosion there, while for the low energy wave, you got some deposition there. And here, this is concentration of sediment in the water column. So we can see the deposition here, and here the erosion. So in summary, what we can say is that there is an increasing effort in developing sediment capabilities within CROCO. Patrick, Guillaume, and I, we are working a lot about this, and there were a lot of progress on this aspect in the model. As I said, our focus is more on sandy or wave-dominated environment. And for these cases, we are more and more confident in what happened. And we have, as I saw, even wave result configuration. So there is one, I think, is the test cases. It's kind of, those are nice configuration, but heavy configurations, because we resolve explicitly the wave. But there are still things we are not doing. For instance, we are not, it's not possible to take into account flocculation, meaning coagulation or decoagulation, aggregation or deaggregation of the sediment in the water column. The consolidation, I mean, what I call the mixed bed option, it is there, but it has to be assessed. We've got still stuff to be done, so interaction with vegetation, diffusion of the sediment in the sediment column, the effect of the sediment in the density of seawater. And we should also, we have planned to work on environments which are more, I would say, estuaries and delta, and to have something which is more, which is less linked to only nearshore applications. So I think that it's all for me.
Thank you, Rachid. Questions? Ornella?
Yes, thank you, Rachid, for your presentation. I want to ask, I think the answer is yes, but I want to ask, can I apply this sediment dynamics with a similar configuration, but in deeper environments, such as a continental shelf or terraces on continental slopes?
Yes. Yeah, well, yeah, you can. Actually, it was implemented at the beginning. It was implemented a long time ago in CROCO. And first application of Patrick, that was Minterblas, also, it was in the shelf in California. Actually, it was not a nearshore application at all.
Okay.
So yes, you can do this.
Okay.
We struggled a lot. It was more or less the other way around. It was working at the shelf, and we struggled a lot to have it working at the shore because it was a bit more. There was more phenomenon happening, so we had to work a lot about this. But yeah, of course, you can use it for what we are doing.
Great. I will work on it. Thank you.
More questions? Here, Vera is on the chat. Saying the sediment model feedback has a feedback on the dynamics. Is a two-way interaction or just one way?
With CROCO, well, the sediment will impact the bottom friction, actually, because it will the sediment, the presence of sediment and the roughness of sediment will change in time. So if I come back, I think there. So this is the bottom stress, which is also used well in the model in general as the bottom condition for the dynamic, and this will change because your rugosity here will change. This is one thing, and then if you're doing morphodynamics, it will have an impact also on the dynamic because your bathymetry will evolve.
Orlando asking if this can be studied for desalination brines from desalination plants. Sediment.
I don't. Well, actually, I have no idea how it works. I mean, desalination brines. I would. I know. I would. Eventually, I don't know. It's something we can discuss. For me, I would see this much more like passive tracer than sediment, but it's unclear to me. I mean, I know. Well, it depends. Well, actually, it depends if what happens with brines, if they tend to deposit or not, and to be eroded again. And I have no idea about this.
Then Sebastian Barra asking if coastal defenses can be added to CROCO.
Yeah, it would be nice, actually, because when we did it like this, for instance, here, those are coastal defense. We did it on other places, but it's not standard. You know, when we put this, we change the mask, something like this, very quickly. It's something so it's feasible, but we would like to have something like a tool or something to be able for users, because it's a question a lot of users from your show are interested by this. So to be able to change, to have this easily as an input.
Luciana Lim was asking about if concentration, size of sediments can be defined.
Yes. Yes, the response is yes. For instance, it was, for instance, there you have two sediments with different characteristics. So it really depends where you, I mean, to me, one problem there is very often you don't have data for sediment, at least in my case. But something we do very often is to put one coarse and one light one. like for instance, the sand and the silt one. So you got usually the silt, which stay more in the water column, and the salt, the sand, which is deposit. But yeah, you can put as many as you want, but then it comes with a cost at the end. It's like geochemical model. It's you have another tracer equation when you use it, but yes, you can do it.
The spatial distribution of this has to be set.
Yeah, it's the same. We can be read well. So I don't remember very well how it is done. Ideally, you could read an input file with the initial distribution of your sediment. So I don't know if it is the case or not currently. I know we do it in some analytical routine, but I don't know if there is a counterpart to read an input file. But anyway, it's something. If it's not something, we will have.
And finally, there is a passive tracer module, no, in CROCO?
Yes, there is. You can
Okay.
does CROCO. I don't know if there are other questions or.
No, I think let's stop for 10 minutes and then
Yeah.
we go to the final